Hello everyone, thank you so much for coming out to this evening's session of the Berkeley Forum. We're really happy to have you all here. I know it's a little bit cramped, but hopefully you all can make more friends in the small space. And just before we get into the introduction of tonight's speaker, I would just like to remind all audience members to please close all laptops and silence all cell phones. I am Tanya Mahagwar. I am the president of the Berkeley Forum, and the Berkeley Forum is a nonpartisan student-run organization that hosts talks, debates, and panels for the Berkeley campus and community. And everything you see here, from student photography to videography to event moderating, is entirely student-run, and it could not work without the efforts of our tireless student staff. So this is just another example of the great work that they put on. And for tonight's event, we are honored to have Dr. Hasini Jayatilaka, who grew up in Sri Lanka and pursued her BS and PhD in chemical and biomolecular engineering at Johns Hopkins University. She's the head author of a study on biochemical signaling in metastasis and on potential drug treatments for slowing down the process, and was previously a postdoctoral fellow at Stanford University. She has given a TED Talk and was featured in Forbes. So without further ado, please welcome Dr. Jayatilaka.
So good evening, everybody. Thank you for being here tonight. I know we're in a tight space, so thank you for huddling up and coming here to sort of listen to me talk, and hopefully I'll make it worth your while. So I'm very excited to be here. It's been a while since I've done a talk like this, but I know I'm also a little bit nervous. But I am ready to sort of share my story, where I started off as an undergraduate student 10 years ago, and today I'm a speaker at the Berkeley Forum. So this is very exciting for me. I want to start off by sort of asking you a question, and I want to ask how many of you are undergrads in this room? Raise of hands. Okay, wow, awesome. Thank you for being here. And how many are freshmen and sophomores? Oh wow, okay, cool. So 10 years ago, I was a sophomore, or actually a freshman, just like you, sitting at the back of a seminar just like this, when my life changed completely, because I had an idea which sort of led to the rest of my career. And so 10 years ago, I was a young, naive Sri Lankan girl, and I had just moved to the States to pursue my undergraduate studies. And I initially started off as pre-med, because everyone at Johns Hopkins is pre-med. And I was just ready to sort of dive in and go into medical school. And I thought I had my whole life planned out 10 years ago. But to be honest, I was pretty lost, because I had no idea what I wanted to do with my life. I graduated at the top of my class at high school. And while most of my peers knew kind of exactly what they wanted to do, I really didn't. And so when I came to Johns Hopkins, I started taking a lot of random classes, trying to figure out what my path was. And one of the classes I took was Introduction to Chemical Engineering, which was a really fun class because it showed me sort of the different careers I can pursue as a chemical engineer. And it was where I, for the first time, met my future PI, Dr. Denny Wirtz. And he was so passionate in the way he talked about cancer metastases. And he had this novel approach to sort of studying this process. And so I was very, very, very interested in sort of his work. But I didn't want to join his lab, because I had just moved to a new country, just settling in with my classes, and I was just figuring things out. And so at the end of my freshman year, I was like, okay, I'm going to email Dr. Wirtz, and I'm going to join his lab, I'm going to do amazing cancer research, and that's going to be my path. And I emailed him, and he just didn't respond back. And so I was like, okay, I'm going to be super persistent, and I went to his office, and he had just started a meeting, so I was like, okay, I'm going to sit outside, wait for 30 minutes, meet him, hunt him down, pounce on him, I'm going to join his lab. I sat outside his office for 2 hours, waiting to meet him. And I finally met him, and I said, I really, really want to join your lab. I love your work, everything, worshipped him. And he was like, fine, I will let you join. And so I started in his lab, working on metastases, which let me give you a little bit background about it. So metastases is the spread of cancer from a primary site to a distal site through the circulatory or the lymphatic system. So it's responsible for 90% of cancer-related deaths. So for instance, a female patient with breast cancer doesn't succumb to the disease simply because she has a mass on her breast. She succumbs to the disease because it spreads to a different part of the body, which causes it to be unresectable or untreatable. And so Dr. Wirtz had this novel concept of using engineering principles to sort of understand the process better, and so allowing us to develop better therapeutics against it. And so I started off studying tumor cell migration, which is the most commonly studied mechanism of cell movement. And what he was doing was sort of putting these metastatic cells in a 3D collagen-1 matrix. So the cells in our body are encapsulated in this jelly-like substance called the extracellular matrix, which is predominantly made of collagen-1. But most of the studies that have been done on cell movement have been done on flat plastic dishes. Now in our bodies, cells are not stuck on plastic dishes, right? And so the phenotypes or the shapes or the movements or the behaviors, everything we're seeing on this flat plastic dish really doesn't recapitulate what we're seeing in our bodies. And if you look at cell movement, you can see in this particular instance, the cells on the 2D flat plastic dish are very different to the 3D cells placed in 3D. In 3D, they have sort of this elongated body, like sort of arms, we call them protrusions, which they like throw out and they hold on to fibers in the collagen-1 matrix and pull themselves through this matrix, and that's how they move. Whereas in 2D, they're kind of like a slug, where they're like, moving on the dish, and they don't move as fast either. And so it was very interesting for me to sort of look at these movies. It was a very menial task of just watching these cells move every single day as an undergraduate student. But it was also really exciting to contribute to this work. And so part of my work was sort of looking at these arms called protrusions and characterizing the topology of these protrusions. And so basically, my life when I joined the lab was counting up to 4. So in a particular time interval, I had to count how many protrusions and how many branches came out from these arms and figure out how it correlated to cell movement. And basically, it would be just 1, 2, 3, 4. But it was fun. And it was also during this time that I attended a seminar similar to this, where I went to see Professor Bonnie Blaisler from Princeton University speak. And she talked about this phenomenon called quorum sensing, which was basically bacterial cells performing a concerted action at a particular time point. And it was then that this light bulb went off in my head, and I thought, I see these in the movies that I analyze every single day. And I was like, okay, I'm really excited. I'm going to go back to my dorm room. I'm going to Google this and see what exactly happens in cancer cells, because I was just interested in learning more. And what I found later on was nobody had studied this. Nobody had seen this in cancer cells. They had seen it in respect to sort of collective cell migrations where the cells were stuck to each other. But they had never seen it at a single cell level where the cells weren't in contact with each other. And so I went up to Dr. Wirtz and I was like, hey, I have this idea. And he was crazy enough to agree to let me study it. And so as a sophomore in college, I came up with this hypothesis that cancer cells can proliferate and increase their local cell density, which can lead to a change in the secretomic profiles, which then leads to an increase in cell migration. It sounds complicated, but really it was a very, very simple hypothesis. And then we performed a very simple experiment where we basically placed cancer cells of a known density in a collagen-1 matrix. We let them grow and move for a period of 5 days. And then we measured the cell migration and we measured other parameters. And what we found was when the cell density increases, you can see that the cell speed increases. And this was something that had not been seen before in our field at the time. So then it was a matter of asking whether this was sort of a phenomenon of just these secreted proteins collecting over a period of 5 days, or was it in fact sort of this physical phenomenon where it was based on local cell density? And so we answered that question by measuring the distance between cells and figuring out the local cell density and placing those exact densities in different collagen-1 matrices. And so here we did that, and we use this highly metastatic cell line called HT1080 wild type, which is commonly used in migration studies. And what we found was as the local cell density increased, you can see an increase in cell speed. And this was true when you looked at other migration parameters such as persistence distance and invasive distance. And so this was sort of the very first step of what was, what then transpired to be like my discovery. But at this time, we called it cell density dependent migration, but that was a really difficult thing to say. So we would call it the Hasini effect. And so we then conducted so many more experiments to sort of look at the Hasini effect. And what we found was that this Hasini effect was unique to metastatic and tumorigenic cells. So we really did not see this in normal cells and non-metastatic cells. And so this, again, was a very, very unique observation. And so at this point, I had come to the end of my undergraduate degree. And we were sort of figuring out what do we want to do next. I had to sort of decide whether I wanted to hand this project off to somebody else or I wanted to go to grad school and do a PhD on it. And so honestly, at the end of my junior year, I really hadn't planned anything. I did my MCAT and I was ready to apply to medical school, and then I just decided I didn't want to. And Dr. Wirth was kind enough to tell me, well, would you like to do a PhD with me? And so he took me into the program. I applied in the program. I got accepted, surprisingly. And he took me into the program, and this is what we worked on from day one of my PhD. And so what we did then was sort of form these collaborations at different universities with professors from different fields. And we were able to discover that these two signaling molecules called interleukin-6 and interleukin-8 were responsible for the Hasini effect. And what we were able to show as well is if we were to block the binding of IL-6 and IL-8 to their receptors, we could essentially slow down metastases and we could stop cancer cell migration. And so we wanted to, and all these studies had been done on the dish in our 3D collagen 1 matrices, which we were confident would sort of represent what we saw in preclinical studies, in mouse models, as well as in the human body. And so we went ahead and we did preclinical testing in a breast cancer model in mice. And what we found was that our treatments where we blocked the binding of interleukin-6 and interleukin-8 to its receptors really had no effect on tumor growth, which was really sad because that was the only thing we were measuring while the experiment was happening, and it seemed like it had no effect. But at the end of the experiment, what we found was that we had decreased metastases to the lungs, liver, and the lymph nodes, which are major sites of metastases in breast cancer. And this was an incredible finding for us because we had not only separated the fact that cancer cell migration and proliferation are completely independent of each other. Because current thinking is, if you stop tumor growth, you can stop metastases. But that's not true. You can have metastases even if you have the tiniest tumor. And the fact that we were able to solely target metastases was significant. And so at this point, we had sort of discovered this whole mechanism of blocking metastases completely independent of tumor growth. And that was really exciting. And so this was sort of the mechanism that we discovered through a lot of work, and this was about 5 years later that we had discovered this mechanism and we were able to publish it. And our significant finding was this mechanism of interleukin-6 and interleukin-8 binding to their cognate receptors and increasing cell migration as a factor of local cell density. But we also showed that this cocktail of drug that blocked the binding of IL-6 and IL-8, which is tocilizumab and referexin, could have a significant effect on decreasing metastases in breast cancer. And so the Hasini effect was published in 2017, May, and I was very fortunate to be able to publish in Nature Communications. I know a lot of people don't really get to publish in Nature journals as their first publication, but I was very fortunate enough to do that. And we actually had a lot of attention because in our first week, we were one of the most sort of viewed articles of that week, and in our first week we had over 3,500 views. And so we had a lot of fun with it as well. We also promoted it like crazy on Twitter, which is what academics do these days. And one of the things that we did, because at this point, Dr. Wirtz had been promoted to Vice Provost of Research at Johns Hopkins. And so we were having a lot of fun with it, and we wanted to see him dance to a rap song if we got over 3,000 views in our first week. He did dance, but this was sort of his version of dancing, real dad dance, and we are not allowed to show the video of him dancing to everybody at this point, which is sad. We're still working on it. But it also came with a lot of fun stuff for me and a lot of exposure for me. I was able to do this wonderful TED Talk that's online that you can see more, where I talk about the work and the power of collaboration. And I was also able to sort of use my platform to lobby US representatives in the House as well as the Senate to increase funding for NIH funding, especially for immigrants and women just like myself, which we were successful in doing that year. And I am also an advocate for women in STEM, and that allowed me to sort of talk more about the impact of having women in STEM and the importance of diversity in STEM as well. And this work also gave me the opportunity to be named as a Forbes 30 Under 30 in 2019. So it was all very exciting, very cool. Just everything that came up from just a simple idea that I had when I was sitting in the back of a classroom like this, when I was just 20 years old. But then, what came next? It was like, cool, so what? I've done all this cool work, I've had these amazing opportunities, but what does it mean? If I was a patient and I had this mass in my body and I was given this cocktail that I had developed, and my physician was like, you're gonna be fine because you're not gonna have any metastases, but my mass kept growing, I think I'd be very, very upset. And so what I thought about next was, how do we sort of use this drug cocktail, how do we sort of use this finding and really make an impact on patients' lives? And for me, the answer was, how do we concurrently target tumor growth and metastases? And so for that, we went back to the drawing board, and we wanted to look at the data that we had already generated, and we found new partners to work with at Yale University, as well as this university in Israel called Biomolecular. And by these collaborations, we were also able, for triple-negative breast cancer at least, to detect another receptor that we could target. So we wanted to add a third drug into our drug cocktail. And so that was cetuximab. And so by doing these experiments, both in the dish and in the preclinical mouse models as well, we were able to develop a drug combination where we can target both tumor cell proliferation and migration, which in a sense means we can target tumor growth and metastases. And so here you can see a little bit of data where we are targeting both tumor growth and metastases, not only in sort of our preclinical mouse models that are used with cell lines, but also with patient samples, patient tumors that are grown in the mouse models. And so this is very exciting work that we've come up with. I also thought about, well, breast cancer is, it is a disease that needs a lot of attention. But what about other highly metastatic cancers, such as pancreatic cancer and ovarian cancer? It was time to expand sort of our reach into different cancers that were not as studied or not as well understood as breast cancer. And so here we came up with this project in pancreatic cancer, where we wanted to use a standard of care drug, which is gemcitabine, currently used to treat pancreatic cancer, but we wanted to combine it with our drug cocktail of tocilizumab and referexin. And so here again, when we did the triple combination, we can see that we affected tumor growth and metastases significantly. And so this is something currently in development, and I think in the next few years, because clinical trials take forever, we are hoping to go into clinical trials with this drug cocktail and hopefully have a significant impact on survival in pancreatic cancer. I also thought about, well, I'm lazy. I don't like to take that many drugs, to be honest. And so what if we came up with a new drug? What if we came up with a new bispecific antibody that can simultaneously target both receptors, the interleukin 6 and interleukin 8 receptor, instead of using a combination of two drugs? And so we teamed up with a protein engineer and we did exactly that. We designed a brand new drug, a bispecific antibody that can target interleukin 6 and interleukin 8. And the advantages of this is that we can first reduce drug resistance, but we can also enhance how the drug responds to cancer cells and the effect that it has. And so by doing this, and now with preliminary testing on the way, we showed that this bispecific antibody, both formats that we have right now in development, perform way better than the combination of the two drugs. And so this is very exciting work that is currently happening with Dr. Wirtz and that I'm involved in as well. And so these are sort of the projects and the ideas that have come out of the simple idea that I had. So after having a very successful tenure, I believe, at Johns Hopkins, I wanted to switch gears. And I also wanted to sort of learn and grow as a scientist. And so I came out here to Stanford University to work in the Department of Pediatrics. And I worked on childhood neuroblastoma, which is the most common extracranial tumor in children. And there really isn't much sort of medicines out there for childhood neuroblastoma. And my goal was to go into a field that was relatively understudied so that I could use my skills and my techniques to understand it better and have a huge impact. And I'm going to skip over this because I have 5 minutes left, but basically through my work, one of the projects that I was able to develop was also discover another new signaling pathway in childhood neuroblastoma that also is involved with metastases. And so by blocking this signaling pathway, which has the TRK receptors, which is another type of receptor involved, we can actually block tumor growth and metastases in childhood neuroblastoma as well. And so it's been a very interesting ride, and so my last 10 years in academia I think have been very exciting, very challenging, but at the same time I've been able to sort of think outside of the box, use my engineering background and come up with solutions to some things that people have been thinking about a lot. And so I definitely did not do all this work by myself. And so it took a village to help me sort of get to where I am today. And these are some of the people that have been involved in my journey. And I'm grateful to have them in my life and hopefully part of my journey moving forward. And with that, thank you so much for your attention. I'm happy to take any questions or comments or concerns that you have.
Round of applause for Dr. Jayatilaka. In all of our events, we always have a short period of student moderating, and I'd like to welcome up our student moderator for this evening, Noah Oppenheimer.
Dr. Jayatilaka, thanks for coming to speak today.
Thank you.
Great to have you. So I want to begin by asking you about the methods that your research follows. You use a specific technique of 3D modeling of cancer cells to conduct your research, as opposed to the traditional Petri dish method that has been used in the past. What, if any, were the key advantages of using this technique to understand the behavior of cancer cells?
Well, I think one advantage is, and I talked about this, was we don't have plastic in our body. And so it's nice not to have that interaction between the cells and the plastic, but to have something else that is actually present in our body, which is either collagen or fibronectin or whatever that constitutes the extracellular matrix. And so to have that is an advantage for us to sort of recapitulate the conditions in our body and sort of study it better. No system is perfect. The organoid system is not perfect. Our three-dimensional system is not perfect. But it gives us a closer insight to what is happening in our bodies.
Now, another issue that you touched on in your speech is the constraint in cancer research having to do with the amount of time, often upwards of 10 years, required to develop and test a new drug. What opportunities, if any, exist to hasten the development of treatment regimens in the future?
That's a pretty difficult question to answer, just because the reason it takes so long is not because we're kind of moving slow, but it's because we're trying to optimize all this for any situation, and we're also trying to validate our findings. I don't believe, like, I want to sort of look at something in one cell line alone and make this very general comment and say all of breast cancer we see this. And now what we're understanding is certain subsets of cancers behave very differently to others. And so we want to make sure that we are thorough in our testing, and whatever we're claiming now in our publications or publicly at these forums is actually true. And that's why it's taking us that long to sort of get our work from the dish to a publication to eventually into a clinical trial, is because we're sort of validating and making sure that what we're saying is actually true.
You talk about how there's a lengthy time frame involved with conducting cancer research. Now, researchers who carry out long-term research often struggle with maintaining stable sources of funding for their work. How, if at all, have these challenges impacted your work in the past or in the future?
So I think funding is a huge issue. There is very limited resources for a lot of people who want to do great research. And it's about, at least for me, I have been very fortunate enough to work with PIs who have been well funded, who through not only NIH but also private foundations. And I think more and more private foundations, even companies, biotech companies, are realizing the value of academic research and now are pumping in more money into those fields, yet there's still so much work to be done. So I think it's about doing good advocacy, talking to people about how important research is, not only cancer research, but research in general for other diseases, and getting people involved and telling them how their dollar is being spent when they, for instance, donate to St. Jude's Children's Hospital when you're at the grocery store. That dollar or whatever that you decide to donate goes a long way in terms of cancer research and making a huge impact on patients' lives.
So you bring up this idea of broadening the scope of who has knowledge of cancer research. Now, although cancer continues to affect 1 out of every 3 individuals, very few actually understand the disease and the relative literature around it. So how, if at all, can we attempt to make breakthroughs in cancer research become more accessible to everyone?
So I think one of the ways we can do it is making journals open access. I was fortunate enough to publish in a journal, Nature Communications, which is open access, which means anybody can access my work. But there are certain journals like Nature, Cell, Science, which are still like based on subscriptions. And I think that makes it very difficult for people to access sort of the literature. And I also think science communication is important, where people, the lay people, non-scientist people, have to be told about this research in a very simple format. And I think now with TED Talks and different forums coming out, people are understanding it more because it's more simplified. But there's still a long way to go in educating the general public about it.
Now, another issue you've mentioned having to do with cancer research in the past is the lack of resources available to people or researchers in places like your home country of Sri Lanka. What, if any, are the implications of this on healthcare research in those countries?
I think it's huge. One case that was brought up this year to my attention was this famous doctor in Sri Lanka, pediatrician in Sri Lanka, was talking about doing a clinical trial where he wanted to increase the dose of chemotherapy given to children. And he was running this big clinical trial, making a huge deal of it. And this was completely incorrect, because right now what we're doing in pediatric cancers is actually lowering the dose of chemotherapy, because chemotherapy has a huge effect on these children's lives. It's very toxic to them. And the fact that this particular pediatrician was being very responsible in his sort of background research and conducting this clinical trial, and there really isn't much regulation on these clinical trials, was really sad. And so I think it's up to governments and it's up to sort of international bodies to be able to regulate some of these research that's going on and really educate the public about what kind of work that we're putting out there.
Now, turning more toward looking at your research specifically, a commonly cited concern with cancer treatment is the high cost incurred by patients and their families. So what implications, if any, does research like yours, which is more focused on targeting a specific aspect of the disease, have on these costs?
I mean, it's going to be, if my sort of, say, antibody was to be translated into the clinic in the next few years, it's going to be very, very, very expensive. And this is it's sad that it's so expensive, but it's also 10, 15 years of work that had been going into it. And the fact that we're getting more and more specific with our therapies is the reason why it's so expensive. And I've been fortunate enough to work at Genentech and see sort of the other side, where it's pharma companies developing drug treatments. And there's a lot of controversy where people are like, pharma companies have all the answers, they have the cure, they're just withholding it from us. But the fact is, like, their research is very similar to academic research. They want to understand these targets, they want to understand the biology so that they can create the next big thing and sort of cure human diseases. And that is just taking a lot of time, it's a lot of resource, and it's a huge investment by everybody. And so I don't really know what the answer is of lowering the cost of these therapies, but I know that some of these costs that are being incurred are necessary just because of the development time and everything that goes into it.
Well, one issue is obviously the cost. Another is the actual effect of the treatment. So with recent advances in targeted cancer technologies, like the one you discovered that selectively can inhibit the growth of cancer cells, how optimistic are you that we can move away from painful therapies like chemotherapy to more targeted and patient-friendly alternatives?
I am mildly optimistic, and I say this because a lot of the clinical trials that are going on right now, we can't necessarily run a clinical trial without a standard of care therapy as a backbone, because we cannot withhold a chemotherapy from a patient. What we can do is add on to the chemotherapy and see what effect there is. If we withheld the chemotherapy and our drug that we're testing does not work, then we've essentially withheld care from the patient. And that's not what we want to do. And so everything that's been tested, even immunotherapies right now, are used in combination with chemotherapies. I think the level that we use chemotherapies will decrease, the dosing will decrease, but I don't necessarily see us moving away from using chemotherapies in the next 10 years or so.
You talk about how your work has the potential to affect other research and other types of treatments. Now, unlike the work you conducted, most disease-centered research in the past has focused on symptom reduction. Given the difficulty in isolating the complex pathways that govern disease function, do you believe the more bottom-up approach you take is a sustainable one in the long run?
I think so. I think there are a lot of, even now, there are a lot of therapies that work on patients. And if you think of pediatric patients, we're just kind of pumping them with different immunotherapies or chemotherapies, and we're hoping for the best. And we're seeing really good outcomes with immunotherapies, for instance. But we don't know the exact mechanisms that are being affected by it. And so when relapse disease, when the disease comes back, we have no idea why. And that's where sort of a basic biologist like myself comes in and sort of explains what was targeted, what wasn't targeted, and how we can sort of stop relapse in the long run. So I think both approaches have sort of their value, but I think we need both parties to sort of make a therapeutic very successful. And so that's where the value of basic biologists come in.
This will be my last question before I move on to further questions from the audience. Now, you found that your work on interleukin 6 and interleukin 8 have therapeutic potential in specific types of cancer, like sarcomas and carcinomas. Do you see any future relevance between your work and other types of cancer, like leukemia or melanoma?
Yes, I do. I don't necessarily know if it's going to be interleukin 6 and interleukin 8, but I think there is value to exploring how soluble factors such as interleukin 8 and interleukin 6 are responsible for relapse disease. Some of my work, which I didn't talk about in childhood leukemia, show that interleukin 16, which is still part of the cytokine family, has an impact on relapse disease in childhood leukemia. And so by developing more targeted therapies against interleukin 16 and maybe doing a combination therapeutic with it, we can potentially stop relapse disease in leukemia, childhood leukemia, which is 90% cured, by the way, because of immunotherapies. But the 10% is what we're trying to figure out, and we're hoping with my discovery with interleukin 16 that we will have an effect on this 10%.
Thank you so much. So to open it up to questions from the audience. Yeah.
So I was wondering specifically for the drugs you talked about that target the IL-6 and IL-8 receptors, how do you make sure they're specific to the tumor?
So the IL-6, the anti-IL-6 is a monoclonal antibody, and so we know that it's directly targeting the IL-6 receptor. It's also used in it's used to treat rheumatoid arthritis right now. So it's a drug developed by Roche, and so they are very accurate with their targeting mechanism. With IL-8, it's actually a small molecule that's in clinical trials against breast cancer. We've done testing with it in terms of targeting, but it does have certain off-target effects, just like any other drugs. And that's why we kind of thought about developing this bispecific antibody, which can be more accurate in terms of targeting.
I've got a quick follow-up. How exactly is the bispecific antibody produced?
So right now we're producing it in bacteria because it's a small-scale production. But when we move into large-scale production, I think it's going to be more of a synthetic antibody molecule.
Other questions?
Is the relationship that you found between local cell density and the motility of the tumor cells something that exists in all metastatic cancers, or only the traditionally highly metastatic cancers?
We believe it's all metastatic cancers, so we've tested it so far in pancreatic, I believe in U87, which is brain cancer. We've tested it in ovarian cancer, a lot of different cancers, and so we believe that there are a subset of cells that do have this receptor, high interleukin 6 and high interleukin 8 signaling, which causes metastases. So we believe it's unique to all metastatic cancers.
Did this come up in your research with neuroblastomas?
It did, but the subset that I was looking at was very specific, and so I was looking at this molecule called synaptophysin, and so it was more about finding a biological signature, which then I could translate into sort of this biomarker, and biomarkers are sort of these sets of proteins we can look at in different patients and select certain patients for clinical trials. And so with the synaptophysin, that was a biomarker that we used. But we did not look at interleukin 6 and interleukin 8 because this was a new project and I was trying to spread my wings and fly away from IL-6 and IL-8. You can ask me anything you want about my undergrad, about anything.
What was it about Stanford that attracted you?
Well, Stanford the name, Stanford the place, Bay Area, really cool. Everybody wants to move to the Bay Area, right? They don't know how expensive it is or how hard life is. No, I think I picked Stanford because I felt like at the end of my PhD, I had this gap in my knowledge, which was learning about proteomics, high dimensional proteomic modalities. And I wanted to work with mass cytometry, CyTOF, which was sort of born at Stanford. And I wanted to work with Dr. Gary Nolan, who is one of the godfathers of CyTOF, ended up working with one of his students. And that was the reason I went to Stanford, because I wanted to learn more. I wanted to become more of a well-rounded scientist. And so the past 2 years have been not only working with CyTOF, but also this new technology called MIBI. And that has allowed me to grow and become a better scientist, hopefully.
Hi, what is your favorite part about your work?
My favorite part about my work is the fact that it challenges my curiosity. You know, the fact that it's always another question to answer. And it's always these open-ended, crazy questions that drive you crazy, and you don't really have a correct answer for it. But that is one of my daily driving forces. But also, I love the fact that 10 years down the line, the bispecific or this crazy combination that I developed could have a huge impact on patients' lives, and that is exciting for me and what keeps me going.
I was just wondering, did you have any difficulties throughout this process about being an international student?
Oh yes, it's been an interesting ride. When I first came, it was adapting to this whole different culture. It's very different to how I grew up. Even adjusting to sort of the American school system was very difficult. But it was all about having the right people in my corner. Definitely a lot of good professors who supported me and good friends who taught me from how to, who took me to my first Taco Bell and I was like, here's a Taco Bell. And then were appalled when I was like, I've never had a Twizzler in my life, which I still haven't had a Twizzler in my life, but they're like, here's a Twizzler, eat it in front of us, tell us what you think. And to this day, there are certain things where I'm like, oh really, is that a thing in America? Okay, that's cool. So as an immigrant, as a woman of color, there are always challenges that you face, as I face. But it's all about how you approach it and how you decide you want to face it and move forward.
Are the IL-6 and the IL-8 primarily produced by immune cells or by the tumor itself?
By the tumor cells themselves. So conventional thinking has been that the immune cells produce these interleukin 6 and interleukin 8, but what we're showing is the cancer cells are just like, I don't care if I get it from the immune cells, I don't care if I get it from the fibroblasts, I'm going to produce it myself and I'm just going to have a great time and I'm going to move and thrive and just destroy this body. And so that was also part of the unique finding.
Do you know why the tumor cells would produce them though? Because aren't these like immune aggregating cells that would pull in the immune system?
Well, I think they produce it because they're just like any other cells in our bodies, because we haven't figured out, well, it depends on the origin of the cells, right? So breast cancer, I think normal breast cancer cells do produce interleukin 6 and interleukin 8 in small quantities, but when they become cancerous, I think they go into overdrive. And so that's what we're seeing. And that's another field that really hasn't been explored, which is secreted proteins. And that's something that my collaborator at Yale is working on, and that's what we're trying to understand. And I think there is a lot of value in looking at secreted proteins and their effect.
Over the past few years, one struggle that some scientists have cited is the lack of funding, particularly from public institutions, towards this kind of funding. So what has been your experience with overcoming those challenges, and what kinds of avenues would you advise aspiring scientists and researchers to pursue in order to get the funding that they need?
So for me, it's all about doing smart science. It's not about doing a lot of science. So it's about picking the right experiment to do and sort of using your resources wisely. It's also about being smart about like what experiments do you need to apply for more funding, to show more impactful work, to show the reviewers of your grant that you're actually going to cure cancer and that the money they give you is going to have a huge impact. So I think just using your resources widely has been what I have been practicing and what I have been taught. And I also think going outside and looking for funding, there are a lot of funding opportunities that I feel like a lot of researchers, students don't really know about. Like for instance, for undergraduate students, there's a lot of resources that you guys can turn to and apply for grants and do really cool work, like whether it's during the year or over the summer. And so finding those resources. So for instance, Stanford and Johns Hopkins have their own funding pages where you can go online, and if I say I'm an early career researcher, I can look at I think 200 different opportunities for funding from not only NIH but also private institutions. So it's all about getting out there and really looking at the resources available to you and sort of taking advantage of those resources.
Great, well, that's all the time we have for questions. Thank you so much for speaking.
Thank you. Thank you for having me. And thank you for being here.
I'll now invite our president back up to the stage.
Thank you so much to Dr. Jayatilaka and Noah for a wonderful moderated section. At all of our events, we always gift our speaker with a custom poster from our design team.
Cool. Thank you so
this is
much.
yours.
Thank you. Oh, sweet.
Thank you all so much for taking the time out of your evenings to make it out to tonight's event. If you all have any feedback, please use the following form, tinyurl.com/Berkeley Forum, to provide us with any feedback so we can optimize our events moving forward. And also, this is the last event of our fall 2019 lineup, so I would like to thank all of you for your continued support throughout this semester. And I would especially like to thank our student staff for all of the hard work, the drive and the passion that they've put in these past few months. The work that they do is truly awe-inspiring, and the community is certainly better for it. I know I am. So a huge round of applause for them. And more information about our spring 2020 lineup will be available at the beginning of next semester. So I hope to see you in the future. Thank you.